Good evening, everybody. I want to spend a little bit of time on a problem that intrigued a well-known YouTuber, Michael Penn, mathematician, educator. Um, it's about the greatest common divisor or the highest common factor. Now, a lot of you might recognize these as the Fibonacci, two Fibonacci numbers. These are four-digit Fibonacci numbers. I think they use notation F19. I believe this is the 19th Fibonacci number. Not 100% sure, but that's what my memory. I didn't go to the trouble to write it down, but this is what I remember. Okay, and it turns out these are consecutive Fibonacci numbers, and it turns out that they take the longest of any other numbers, I believe, is what he's trying to convey right down here. And there's a result by Gabriel Lame that I'll talk about briefly when I'm done with this. But let's just write down what we mean by the Fibonacci sequence. So it's defined, the first two are defined to be 1 and 1. Then after that, is the next term is always the sum of its two predecessors. Okay, the sum of the previous two terms. So 1 plus 2 is 3, 3 plus 2 is 5, and you see how it goes. And this has been known to model rabbit populations, believe it or not. I don't know how that works really, but the claim is that it was motivated by modeling rabbit populations based on certain initial conditions, ideal conditions. Now, so there you go, and I'll just quit writing. But notice that a general term in the Fibonacci sequence, I'll just go ahead and arbitrarily use K as a subscript. The kth term, f sub k, is equal to f sub k minus 2. And I'm doing this for a reason. There's an interesting little side result here that I wasn't aware of really. This would be plus like this, I guess. Okay, so this is saying a particular term is equal to the sum of its two predecessors. Now notice here, if you divide through by, I guess, k sub 1, in other words, if you get, well, I'll just write this down, f sub k divided by f sub k minus 1, okay, would equal to f sub k minus 2 over f sub k sub 1 plus 1, okay? But you can see that that's going to force this number, this ratio, to be between. In other words, what I'm trying to say is that that forces this ratio to be between 1 and 2. Okay, so up here, hopefully it's a little more readable here. So the ratio of a Fibonacci number and its predecessor has to be between 1 and 2, and I hope I've proven that down here satisfactorily. Okay, but anyway, this is true. This is true, and I think this more or less is a proof of it right here. Okay, but what does that mean with respect to the Euclidean algorithm? Well, I've done it here for you, and most of the work is, you see how you have a 1 here all the way down. You see, you're never going to hack away at this more than just a quotient of 1. Okay, or a dividend, I guess a quotient of 1. Okay, but you can see how many steps this is taking here. Okay, you take the first two, this is f sub 20, f sub 19, you get this. Now notice you will get, if you go down far enough, you'll recognize you just get nothing but the Fibonacci numbers. And so it's not that surprising when Dr. Penn was marveling at this, like, wow, but it just really follows almost immediately from the definition of Fibonacci numbers, being equal, a Fibonacci number is the sum of its two predecessors based on the initial conditions 1 and 1. Okay, so not that surprising, but what I counted right here, I counted 18 of these steps. Let me write that in here. 18 steps. And I'm not going to count them again, but that's what I got on my first count. 18 steps. And I know that Dr. Penn actually grappled with a suitable definition for step, which that's just something to worry about, but he didn't worry about it too much. But notice right here that this result by Gabriel Lame, it goes like this. You look at the smallest number, the number of digits in the smallest number in the process, and that smallest number is 4181. It has 4 digits, and so he claimed that there would be no more steps than 5 times the number of digits of the smallest number involved. Now in this case, the distinction's blurred just a little bit because both of the numbers have 4 digits, but in general it would be 5 times 4, no more than this many steps. And this is a result, I guess it's been proven by Gabriel Lame. I'm not sure if he just waved his hands and called it a conjecture based on a lot of empirical evidence, or whether or not he proved it rigorously. But there's no more than 5 times 4 steps. So in this case, that would equal to 20 steps. And that is consistent with what happened here, because I counted 18 steps. And again, our smallest number has 4 digits. Our largest number has 4 digits. But with his result, if I remember it correctly, says that take the smallest number, count its digits, multiply that by 5, and that will be an upper bound for the number of steps. So that's pretty cool. It doesn't sound like the guy got too rigorous about it. He just used a lot of examples. He probably checked it out for probably, let's say 50 special cases. And that was always true for those 50 special cases. So he inductively concluded his result, or he may well have proven it rigorously. I haven't looked it up. I'll look it up later on. But in any event, I thought you guys would like this because, first of all, you got a juggling octopus here. And second, it's sort of a recreational math problem, I guess you would call it. Fibonacci, people on the plains tell you they've heard of Fibonacci numbers, or if you just meet somebody for the first time and they know you like math, one of the first things they'll talk about is Fibonacci numbers, and also the rule of calculus where you bring the exponent around the front and then decrement, But in any event, this is what I got, and I kind of like this, and you can just see the Fibonacci numbers manifesting very prominently during this algorithm, and of course the terminate condition, or did I leave that out? You got down to 0 right here, right? When you get a 0 remainder, you know that the last non-zero remainder has to divide the original 2. And it would be a very daunting, laborious, onerous task to try to go back and write 4181, or write 1 as a linear combination of 4181 and 6765. To me, that's very tedious, and I don't know if they perfected that any, but I think it's just hard, especially when you have 18 steps where you have to go back and back substitute. But in any event, that is all. Everybody, thank you for viewing.